Imagine that you are looking through the window of a spacecraft as Earth begins to fall away beneath you. At first, the planet is too large to understand. Blue oceans stretch across the glass. White clouds spiral over continents. Along the edge of the world, the atmosphere forms a thin blue line, so delicate that it looks as though it could disappear with a single breath. From this distance, Earth does not seem small. It seems complete. Every person you have ever known is somewhere inside that curved horizon. Every city, every forest, every storm, every road, every familiar room. The entire human story is contained within the bright sphere slowly turning below you. For the first few hours, leaving Earth may not feel frightening. The engines are quiet. The cabin is warm. Air moves gently through the vents. Screens glow with reassuring numbers. The planet remains visible through the window, enormous and brilliant, following you like a silent companion. But the spacecraft continues outward, and Earth begins to shrink. After some time, individual continents become difficult to recognize. The lights of cities vanish. Weather systems become pale streaks wrapped around a blue marble. Then even the marble grows smaller. Nothing dramatic happens when this change begins. There is no alarm announcing that home has become distant. No line appears in space, marking the place where safety ends. The spacecraft simply keeps moving, and the world that built it occupies less and less of the sky. This is where the true nature of distance begins to reveal itself. Traveling through space is not simply a matter of adding more miles behind you. Every mile changes what Earth is still capable of doing for you. Close to home, Earth surrounds you with invisible forms of protection. Its magnetic field turns away much of the dangerous radiation arriving from the sun and the galaxy. Its communication networks allow hundreds of engineers to watch over a spacecraft almost in real time. Its rockets can carry food, water, medicine, and replacement parts into orbit. And when everything goes wrong, Earth is still close enough to take you back. But none of these protections extends forever. The magnetic field weakens. Messages take longer to arrive. Rescue changes from difficult to impossible. Sunlight fades. Machines age without replacement. Eventually, even the star that gave warmth to every human life becomes nothing more than a bright point behind you. The unsettling part is that these protections do not disappear together. They are removed one at a time. Slowly, quietly. At one distance you lose the atmosphere but remain inside Earth's magnetic shelter. Farther out, you lose that shelter but can still speak to people at home with only a slight delay. Beyond that, communication remains possible, but no rescue vehicle could ever reach you in time. Each threshold removes something that once felt permanent. And once it is behind you, space offers no simple way to recover it. This is why the farther reaches of space are not merely more remote versions of the region near Earth. They are fundamentally different places. Near Earth, a damaged spacecraft may still be saved by a launch from the ground. Near Mars, the crew may receive advice only after the emergency has already changed. Beyond the outer planets, a failed component may remain broken forever. Between the stars, a spacecraft may travel for thousands of years without passing close to another world. And between galaxies, even the lights ahead may be moving away faster than any traveler could ever follow. The universe does not become more hostile because it notices that you have arrived. It does not notice you at all. Its laws remain exactly the same. The vacuum does not deepen. Darkness does not become angry. Gravity does not change its mind. What changes is your relationship with the only place that was ever prepared to keep you alive. As Earth grows smaller behind the spacecraft, it is not only becoming more distant, it is becoming less able to reach you. And there may come a point when the planet is still visible, still beautiful, still unmistakably home, yet no longer capable of helping you in any meaningful way. So where does that point begin? At what distance does exploration stop feeling like a journey and begin to feel like disappearance? To answer that, we must begin much closer to Earth, aboard the most distant human outpost ever continuously inhabited. A place surrounded by lethal vacuum, exposed to radiation, and moving around the planet at nearly 5 miles per second. A place we confidently call space. And yet, in almost every way that matters, it is still the final room inside the human world. 400 kilometers above Earth, the International Space Station moves through darkness at more than 17,000 miles per hour. At that speed, it circles the entire planet roughly once every 90 minutes. The astronauts aboard it watch sunrise sweep across the horizon again and again. Day becomes night. Night becomes day. The oceans flash blue beneath them, then vanish into shadow. City lights appear like glowing nerves across the continents, and the thin atmosphere shines around the curve of Earth like a fragile ring of glass. From the ground, this seems like deep space. The station is above almost all of the atmosphere. Outside its walls, there is no breathable air, no pressure, and no protection from the extreme conditions of orbit. A small hole in the wrong place could empty a module. A damaged cooling system could make part of the station dangerously hot. A fast-moving fragment of metal, no larger than a screw, could strike with the energy of an explosive projectile. Nothing about the environment is forgiving. And yet, the astronauts are not truly beyond Earth. They are closer to home than many people realize. If Earth were the size of a basketball, the International Space Station would orbit less than half an inch above its surface. The images from orbit create an illusion of enormous separation because there is no visible road connecting the station to the ground. There are no cables stretching downward, no towers, no bridges. But invisible connections surround the crew at all times. The first is Earth's magnetic field. Deep beneath the planet's surface, the motion of liquid metal in the outer core helps generate a vast magnetic structure extending far into space. This magnetosphere deflects and redirects many charged particles arriving from the Sun and from more distant regions of the galaxy. The astronauts aboard the station still orbit inside this protective region. They receive more radiation than people on the surface, but Earth continues to absorb, redirect, and reduce part of the danger for them. The planet is still standing between the crew and some of the most energetic particles moving through space. The second connection is communication. When an astronaut speaks to mission control, the reply can return almost immediately. The signal travels from the station to satellites and ground networks, but the delay is so small that a conversation still feels natural. Engineers can listen as a problem develops. Doctors can speak directly with a crew member who feels unwell. Specialists on Earth can study live data from individual pumps, batteries, cooling loops, valves, and computers. The crew is surrounded by silence outside the station. But inside their headsets, Earth is always talking. This matters more than it may appear. A spacecraft is not one machine. It is thousands of systems depending on one another. A small change in pressure may suggest a leak. An unusual temperature may reveal a failing pump. A drop in voltage may be the first sign of a larger electrical problem. On the station, the crew does not have to interpret every sign alone. Entire teams on the ground are watching. A person who has spent years studying one particular component may notice a pattern long before it becomes obvious inside the cabin. Advice can arrive while the emergency is still beginning, not after it has already unfolded. The third connection is physical escape. At almost any time, at least one crew spacecraft is attached to the station. It is not simply a vehicle waiting for the next scheduled journey. It is a lifeboat. If the station suffered a failure that could not be controlled, the crew could enter the capsule, seal the hatch, undock, and return to Earth. Depending on the situation and the vehicle, The journey home could take only a matter of hours. This makes low Earth orbit unique. It is the only place beyond the atmosphere where a human being can face a serious emergency and still realistically reach a hospital on the same day. Farther out, this possibility disappears quickly. Near the Moon, returning home requires days. On the way to Mars, it may require months. Beyond the outer planets, no rescue plan exists at all. But on the International Space Station, the door home is always nearby. The fourth connection is resupply. Cargo spacecraft regularly bring food, clothing, scientific equipment, medicine, water, and replacement parts. If a device fails beyond repair, another may be sent. If supplies begin to run low, more can arrive. If engineers discover a weakness in a system, they can design a new component on Earth and launch it into orbit. This means the station is not truly a closed world. It recycles water. It regenerates oxygen. It carefully manages waste and supplies. But its survival still depends on a continuous stream of launches from the planet below. The station may appear to be alone in the blackness, yet it is supported by factories, laboratories, launch sites, ships, satellites, computers, and thousands of people on Earth. It is less like a distant colony, and more like the highest room in a building, whose foundations remain firmly planted on the ground. The walls are thin. The outside is lethal. But every essential service is still connected. Radiation protection still reaches it. Human voices still reach it. Replacement parts still reach it. And if necessary, the crew can still reach home. This is why low Earth orbit, despite all its dangers, does not represent the deepest form of isolation space can create. The astronauts can look through the window and see darkness stretching in every direction, but the planet below still holds them in ways they cannot see. Earth is still beneath their feet, still surrounding their orbit, still listening, still ready to bring them back. Then, one day, a spacecraft fires its engine and changes its path. It does not remain in a loop around Earth. It begins to climb. The station falls behind. The atmosphere becomes more distant. The planet's curve shrinks in the window. And ahead lies the first invisible boundary, where one of Earth's greatest protections begins to weaken. The magnetic shelter does not end with a wall. There is no flash of light when the spacecraft crosses it. But beyond that threshold, radiation is no longer mainly Earth's problem. It becomes yours. As the spacecraft climbs away from Earth, the planet does not suddenly release its hold. Gravity remains strong. Radio signals still arrive quickly. The blue sphere still fills a large part of the window. But one of Earth's most important protections is already beginning to thin. The planet's magnetic field extends far beyond the atmosphere, forming an enormous invisible region known as the magnetosphere. It is shaped by the solar wind, compressed on the side facing the sun, and stretched into a long tail on the night side of Earth. Inside this region, charged particles are guided, trapped, or redirected. Some are driven toward the polar atmosphere, where they collide with gases and produce the quiet curtains of green and red light we call auroras. Those colors are beautiful, but they are also evidence of a battle occurring far above the surface. Every aurora is created by particles carrying enough energy to disturb atoms in the atmosphere. Without the atmosphere and magnetic field working together, more of those particles would reach the ground, the oceans, and the living cells below. For most people, this protection is so constant that it is almost impossible to notice. You have lived inside it from the moment you were born. Every breath, every walk beneath the open sky, every night spent looking at the stars, has taken place beneath an invisible magnetic roof. Low Earth orbit remains beneath much of that roof, but a spacecraft traveling toward the Moon must rise through regions where trapped radiation becomes far more intense. These are the Van Allen radiation belts. They are not solid rings, and they are not perfectly shaped. They are broad, changing zones filled with energetic particles held by Earth's magnetic field. The inner belt contains large numbers of high-energy protons. The outer belt is dominated by energetic electrons. Their size and intensity can change as the sun becomes more or less active. A spacecraft cannot see them. No glowing boundary appears ahead. The crew does not hear particles striking the hull. Yet instruments inside the vehicle record the change. Radiation levels rise. For a short mission, the safest strategy is simple: cross quickly. Trajectory planners guide spacecraft through less intense regions, and engineers use the mass of the vehicle itself as shielding. Tanks, equipment, seats, supplies, and structural walls are arranged so that as much material as possible lies between the crew and the radiation outside. The danger is manageable when exposure is brief. But the crossing carries a deeper meaning. The radiation belts are not only a hazard, they are a threshold. On the near side, Earth is still doing much of the work. On the far side, the spacecraft must begin protecting itself. Beyond the strongest parts of the magnetosphere, two major forms of radiation become central to every deep space mission. The first comes from the sun. Most of the time, the sun appears calm. Its light reaches Earth with remarkable consistency, and its surface changes slowly enough that the human eye would notice almost nothing from one day to the next. But the sun is not quiet. Its surface and atmosphere are controlled by twisted magnetic fields. These fields can suddenly reorganize, releasing enormous amounts of energy. A solar flare may erupt. A coronal mass ejection may throw billions of tons of charged material outward. And energetic particles may race through the solar system at speeds high enough to reach a spacecraft with little warning. If a powerful solar particle event strikes an unprotected crew, the danger is not theoretical. Radiation can damage tissue, increase long-term cancer risk, and at sufficiently high doses cause acute illness. Nausea, weakness, damage to blood-forming organs, and injury to internal systems can begin without any visible wound. The crew may feel nothing as the particles enter the spacecraft. There is no heat against the skin, no smell, no pressure wave, only a number on a radiation monitor beginning to climb. For this reason, deep space vehicles are designed with a protected area, sometimes called a storm shelter. It may not look like a bunker. It can be a small region surrounded by water containers, food supplies, equipment, and other dense materials already needed for the mission. When solar monitoring systems detect a dangerous event, the crew moves into this space and waits. Imagine 4 people pressed close together inside the smallest protected part of a spacecraft. Around them are bags, tanks, cables, and storage compartments, arranged to absorb as much radiation as possible. Outside, the sun looks unchanged. It still shines with the same pale brilliance through the window. The cabin does not shake. The engines remain silent. Yet an invisible storm is passing through the vehicle. The crew can do almost nothing except wait for the instruments to say it is over. The second source of radiation is even more difficult. Galactic cosmic rays arrive from beyond the solar system. Many are produced by violent events, such as supernova explosions. Some are atomic nuclei moving at nearly the speed of light, carrying extraordinary amounts of energy across the galaxy. These particles do not arrive as a single storm. They form a constant background. Day after day, year after year, they pass through spacecraft walls, equipment, and living tissue. Shielding against them is complicated. A thick wall may stop some particles, but high-energy cosmic rays can strike the atoms inside the shielding and break them apart. The collision produces a spray of secondary particles that continues into the cabin. The wall protects the crew, but the wall can also become part of the radiation event. This is why simply adding more metal does not solve everything. Engineers study materials rich in hydrogen, such as water and certain plastics, because they can reduce some forms of radiation more effectively than heavy metals. Future habitats may place water tanks around sleeping areas or use food and waste supplies as part of the shielding. Even then, no practical spacecraft can block every cosmic ray. Some will pass through. The mission must accept them. Near Earth, exposure can be monitored and limited by short missions. On a voyage lasting years, the dose accumulates. One particle does not end the mission. One day does not end the mission. The danger grows through repetition. This is the first great change in traveling outward. Near Earth, radiation is an environmental problem softened by the planet. Beyond Earth's magnetic shelter, it becomes a permanent part of life aboard the spacecraft. Every route must consider it. Every wall must respond to it. Every extra day adds to it. And every crew member carries the record of that exposure inside their own cells. Still, Earth remains close enough to speak. A voice from mission control can warn the crew that a solar storm is coming. Doctors can review radiation readings. Engineers can recommend where the astronauts should shelter. For now, the planet can still participate, but the spacecraft continues outward. Soon, the distance becomes large enough that even light requires noticeable time to cross it. A question leaves the spacecraft. Silence follows. And for the first time, the crew must wait for Earth to catch up with the present. Radio waves move at the speed of light. Nothing carrying information can travel faster. Near Earth, this limit feels almost meaningless. A signal from the International Space Station reaches the ground in a tiny fraction of a second. The delay is too small for a human conversation to notice. An astronaut speaks. Mission control answers. The exchange feels immediate, as though the people on Earth are sitting in another room. But light has a speed, and distance has patience. As the spacecraft travels outward, the space between a question and its answer begins to grow. Near the Moon, a radio signal takes a little more than a second to travel one way. A reply requires the same journey back. The total delay is only a few seconds, but it changes the rhythm of speech. Someone asks a question, then waits. The response arrives after a silence just long enough to feel unnatural. People begin speaking in longer, more complete sentences. They avoid interrupting. They learn to leave empty space between thoughts. The delay is manageable, but it is the first sign that Earth is no longer sharing the same moment. Beyond the Moon, the silence lengthens. At Mars, the distance between planets constantly changes. When Earth and Mars are relatively close, a signal may take only a few minutes to cross the gap. When they are on opposite sides of the Sun, the one-way delay can approach 22 minutes. That means a simple exchange can require nearly 44 minutes. You speak into the microphone. Your words leave the spacecraft as radio waves. For the next several minutes, no one on Earth knows what you have said. When your message finally arrives, the people listening are hearing your past. They discuss it. They prepare a response. Then their answer begins its own journey through the darkness. By the time it reaches you, almost an hour may have passed since the original question. This is not a conversation. It is correspondence. And in an emergency, correspondence may not be enough. Imagine a warning appearing on the spacecraft's control panel. Pressure is falling inside one section of the vehicle. The change is small at first, but steady. It may be a sensor error. It may be a leaking seal. It may be a crack opening somewhere behind a wall. The crew sends the data to Earth. Now the signal is traveling. Mission Control has not seen the warning yet. The engineers who understand the system better than anyone are still unaware that anything has happened. Inside the spacecraft, the pressure continues to fall. The crew cannot wait 20 minutes for Earth to receive the message, another several minutes for specialists to study it, and 20 more minutes for their recommendation to return. They must act. One astronaut closes a valve. Another isolates a module. Someone checks the oxygen supply. Someone else searches for the source of the leak. The crew is making decisions while Earth remains trapped in an earlier version of the event. Eventually, Mission Control receives the first message. On the ground, teams begin analyzing a spacecraft that no longer exists in the condition they are seeing. The valve they are studying may already be closed. The module they are discussing may already be sealed. The crew may have found the leak. Or the situation may have become much worse. The response from Earth is carefully written, technically correct, and based on information nearly an hour old. When it finally reaches the spacecraft, the astronauts may read advice for a problem they have already solved. Or for a moment they have already lost. This is how distance changes the role of mission control. Near Earth, the ground can participate in events as they happen. Near Mars, the ground becomes an advisor to the past. It can still provide expertise. It can still analyze complex data. It can still help the crew plan future actions. But it cannot reach into the present. The present belongs entirely to the people inside the spacecraft. This change affects every part of the mission. Medical decisions cannot always wait for a flight surgeon on Earth. Navigation problems may need to be corrected before the ground can approve the maneuver. Computer failures may have to be diagnosed by people who were not originally trained to understand every detail of the software. A crew member may have to choose between two dangerous options, knowing that the best experts in the world will not even hear about the problem until after the choice has been made. For decades, human spaceflight has depended on the idea that astronauts and mission control form one team. The people in orbit perform the physical work. The people on the ground provide the depth of knowledge. Thousands of specialists become an invisible extension of the crew. On a Mars mission, that extension is stretched across millions of miles. It does not break completely, but it can no longer move in real time. Future crews will need far more independence than any astronauts who have lived aboard the International Space Station. They will need computers capable of diagnosing failures without help from Earth. They will need medical systems that can guide treatment locally. They will need detailed repair instructions, spare software, engineering databases, and training broad enough to prepare a small group of people for problems no one predicted. They will also need to trust one another. On the station, a disagreement can be settled by calling the ground. On the way to Mars, the crew may have to make the decision themselves and explain it later. This may sound like a small operational change. It is not. For the first time, a human crew would become the highest authority in its own world. Earth may advise. Earth may warn. Earth may disagree. But Earth cannot take control quickly enough to matter in the moment. There are times during a Mars mission when communication may become even more difficult. When the Sun moves between Earth and Mars, radio signals must pass close to the solar atmosphere. The charged particles around the Sun can interfere with communication, making transmissions unreliable. During these periods, mission planners may reduce or temporarily suspend certain commands. The crew is not completely disconnected, but Earth becomes quieter. The people inside the spacecraft know that for a time, the star that gives them light is also standing between them and home. Even when communication is clear, the delay changes human relationships. A message from a family member is already old when it arrives. The person who recorded it has continued living during the time it spent crossing space. A child may describe something that happened yesterday. A partner may ask a question that cannot be answered until much later. A disagreement cannot be resolved in one conversation. A moment of loneliness cannot be met immediately by a familiar voice. Every connection must pass through the same distance. The crew still receives words from Earth. They still hear laughter. They still see faces on recorded video. But the people in those recordings are never speaking from the present. Earth becomes a place of delayed emotions, a place that loves you from several minutes ago, a place that worries about dangers you may have already survived, a place that answers questions your current self may no longer be asking. This is the second great loss of traveling outward. The first was physical protection. Now the crew begins to lose shared time. Earth is still visible as a bright point in the sky. Its antennas can still hear the spacecraft. Its scientists can still send instructions. But no matter how powerful the transmitter becomes, no matter how large the receiving dish, no one can remove the delay. It is not a weakness in the equipment. It is not a problem waiting for better technology. It is built into the universe. And as the spacecraft travels farther, the silence between messages only grows. At Jupiter, a reply may take well over an hour. At Saturn, several hours. At Neptune, an entire working day may pass between a question and its answer. Beyond the solar system, messages may take days, months, and eventually years. There is no sudden moment when communication ends. It simply becomes slower until the word communication begins to lose its meaning. For now, near Mars, Earth can still offer advice. But there is another form of help that distance removes far more completely. A voice may cross millions of miles. A rescue vehicle cannot. And if something happens to a human body in the darkness between planets, the nearest hospital is no longer merely far away. It is unreachable. On Earth, distance is usually measured in time. A hospital may be 20 minutes away. A rescue helicopter may need an hour. A ship in the middle of an ocean may wait longer, but even there, help exists somewhere beyond the horizon. Modern life has taught us to believe that almost every emergency can be reached. Not always in time, not always successfully, but reached. Deep space quietly removes that belief. A spacecraft traveling toward Mars may still receive instructions from Earth. Its crew may still hear the voices of doctors, engineers, and family members. But no voice can carry medicine. No radio signal can set a broken bone. No message can replace lost blood. Information can cross the distance. Help cannot. Once a spacecraft has committed to an interplanetary trajectory, it cannot simply stop, turn around, and fly home. Spacecraft do not travel through space the way cars travel along roads. They move along paths shaped by gravity, velocity, fuel, and the changing positions of planets. A vehicle bound for Mars is not pointing directly at the place where Mars appears at launch. It is traveling toward the place where Mars will be months later. The spacecraft and the planet are both falling around the Sun. Returning to Earth requires another carefully timed path, enough propellant to enter it, and an Earth that will be in the correct place when the vehicle arrives. The crew may be only a few weeks into the mission and already unable to come home for many months. Nothing has locked the door. Physics has simply moved the doorway somewhere the spacecraft cannot reach. This changes the meaning of every medical problem aboard the ship. On Earth, appendicitis is dangerous, but usually treatable. A patient is examined, scanned, anesthetized, and taken into surgery. Inside a spacecraft millions of miles from home, the same condition becomes an entirely different event. There is no operating room waiting nearby. There is no specialist team. There is no blood bank, no intensive care unit, and no second ambulance carrying equipment that someone forgot to bring. there is only the crew, whatever medical knowledge they possess, whatever instruments were packed before launch, whatever medicines have not expired or degraded, and whatever decision they are willing to make while the nearest expert waits on the other side of a communication delay. Future crews traveling far from Earth will likely include people with extensive medical training. They may carry compact imaging devices, surgical tools, automated diagnostic systems, and computer-guided procedures. But a spacecraft cannot contain a complete hospital. Every kilogram has a cost. Every piece of equipment takes space, power, maintenance, and training. A machine brought for one emergency may never be used. A machine left behind may become the one thing the crew desperately needs. Mission planners can prepare for common injuries. They can carry antibiotics, pain medication, dental equipment, splints, intravenous fluids, and tools for minor surgery. But the human body has an almost endless number of ways to fail. A blood vessel may rupture, a clot may form, an infection may resist the available drugs, a heart rhythm may become unstable, a crew member may fall during exercise and strike their head against the cabin wall. A tooth may crack, a kidney stone may begin moving, an allergic reaction may close an airway. On Earth, these events call different specialists. In deep space, they call the person sleeping in the next compartment. Imagine that someone becomes seriously ill halfway to Mars. The first symptoms are uncertain: fatigue, pain, a low fever. The crew begins an examination while sending the data home. By the time doctors on Earth receive the message, the patient's condition has changed. By the time their recommendations return, the crew has already made decisions. They may have started treatment. They may have chosen the wrong treatment. They may have discovered that the problem is something else entirely. The doctors on Earth can help interpret scans and suggest procedures, but they cannot place a hand on the patient. They cannot feel the tension in an abdomen. They cannot smell a chemical change in the cabin. They cannot see the fear that the camera misses when the patient turns away. The person performing the procedure may be a geologist, pilot, or engineer who trained for this possibility years earlier in a simulation. Their hands may remember the sequence. Their mind may remember the diagrams. But this is no longer training. The person on the table is someone they have lived beside for months, someone whose voice they hear every morning, someone whose skills may be essential to the survival of the mission. And the spacecraft continues moving throughout it all. The engines may be silent, but the trajectory does not pause for grief, uncertainty, or surgery. The destination keeps approaching. The supplies keep declining. The other systems still require attention. This is one of the harshest truths of long-duration spaceflight. A medical emergency does not replace the mission. It becomes part of the mission. Even if one person is fighting for their life, someone must continue checking the oxygen system. Someone must monitor navigation. Someone must prepare food, manage waste, inspect power levels, and communicate with Earth. A crew of 6 can become a crew of 5, in a practical sense, even before anyone has died. The sick person cannot perform their duties. Another crew member becomes the caregiver. The remaining 4 inherit the work of the entire ship. Fatigue spreads outward from the patient into every system aboard. Apollo 13 is often remembered as proof that human beings can survive almost any disaster in space through courage and ingenuity. And it was a triumph. After an oxygen tank exploded on the way to the moon, the crew and the engineers on Earth transformed the lunar module into a lifeboat. They preserved electrical power, managed carbon dioxide, corrected the trajectory, and brought all 3 astronauts home. But Apollo 13 also benefited from conditions that will not exist on a mission to Mars. the spacecraft was only a little more than 1 light-second from Earth. Mission Control could speak with the crew almost in real time. Hundreds of specialists could work on the same problem while it was still unfolding. The vehicle carried a second pressurized spacecraft that could be adapted for survival. And the Moon's gravity helped guide the damaged ship back toward Earth. A Mars crew would have no nearby world to swing around and return within days. No second spacecraft designed for landing would necessarily be available as a shelter, and the people on Earth would always be responding to an older version of the crisis. Apollo 13 demonstrated what is possible when a distant crew still has the full intelligence of Earth beside them. A Mars emergency would reveal what happens when that intelligence arrives too late to lead. There is also a more uncomfortable possibility. The most medically trained person aboard may become the patient. A crew can carry 2 doctors, but no mission can guarantee that the correct person will remain healthy. The surgeon may break an arm. The medical officer may become unconscious. The person most capable of recognizing a dangerous symptom may be the one experiencing it. At that point, the crew must rely on written instructions, automated systems, and their own ability to remain calm. Some emergencies will be survivable, some will not. Not because the illness is always fatal, but because the treatment required does not exist inside the spacecraft. This is where space changes the definition of danger. A condition that would be routine on Earth may become lethal simply because it happens in the wrong location. The universe does not need to create a new disease. It only needs to place an ordinary human body far enough from a hospital. Every astronaut who agrees to such a mission will understand this before launch. They will train for years. They will rehearse procedures. They will learn to trust the people around them with their lives in the most literal way possible. But knowledge does not remove the distance. Once the spacecraft leaves, no rescue vehicle can chase it and arrive in time. A second mission launched from Earth would face the same months-long journey. By the time it reached the first crew, the emergency would have ended one way or another. There is no cavalry in interplanetary space. There is only what was packed. What was learned, and what the people inside the ship can do for one another. This is the third great protection lost on the outward journey. Earth can still listen. Earth can still advise. Earth can still care. But Earth can no longer reach through the darkness and bring someone home. And as the crew learns to live with that truth, another danger is already developing around them. The human body may fail suddenly. The spacecraft fails more slowly. Every seal, pump, filter, wire, and moving part has begun to age from the moment of launch. There will be no ambulance for the crew. And soon, there will be no repair shop for the machine keeping them alive. A spacecraft carrying humans to Mars would be more than a vehicle. It would be an atmosphere, a water system, a power station, a waste processing plant, a hospital, a kitchen, a communications center, and a shelter against radiation. It would be a small artificial world surrounded by an environment that provides almost nothing the human body needs. And every part of that world would have to continue working for months or years without a true repair shop, without replacement shipments, and without anyone outside the crew ever touching the hardware again. On the International Space Station, equipment fails regularly. Pumps stop. Computers reset. Valves become unreliable. Filters reach the end of their useful lives. This does not mean the station is poorly designed. It means that complex machines eventually wear down. The difference is that the station can be repaired. Replacement parts can be launched from Earth. New tools can arrive. Engineers on the ground can redesign a component, test it, place it inside a cargo spacecraft, and deliver it to orbit. The station survives not because nothing breaks, but because broken things can be replaced. A deep space vehicle loses that protection. Once the engines send it away from Earth, its inventory is closed. Every filter it will ever use is already aboard. Every spare pump already has a storage location. Every tool, wire, seal, circuit board, medical instrument, and replacement valve must have been selected before launch. Anything forgotten on Earth effectively does not exist. This creates an impossible design question. What should the spacecraft carry? A spare for every critical system would make the vehicle too heavy to launch, but leaving out the wrong spare could turn a minor failure into the end of the mission. Engineers solve part of this problem through redundancy. Instead of one oxygen-generating system, the spacecraft may carry two. Instead of one navigation computer, it may carry several. Instead of a single communication path, it may have backup antennas and transmitters. But redundancy does not make a system immortal. A backup machine is still a machine. It contains seals that age, electronics that absorb radiation, and moving parts that slowly wear. The second system may fail for the same reason as the first. Or it may remain unused for years, only to reveal a hidden problem when the crew finally needs it. In deep space, every machine is also a clock. Some clocks measure hours, others measure years. But all of them are counting down. The life support system carries the greatest burden. A human being consumes oxygen, produces carbon dioxide, drinks water, releases moisture, generates heat, and creates waste every day. On Earth, the atmosphere, oceans, soil, weather, and countless living organisms recycle these materials on a planetary scale. Inside a spacecraft, machinery must imitate a small part of that enormous natural system. Water is recovered from cabin humidity, washing, and urine. Carbon dioxide is removed from the air. Oxygen is stored or regenerated. Trace gases released by plastic, electronics, cleaning products, and human bodies must be filtered before they accumulate. Heat must be collected and moved toward radiators. Waste must be stored, processed, or reused. The spacecraft is constantly cleaning the consequences of keeping its crew alive. No recycling system is perfectly efficient. Some water always escapes recovery. Some oxygen is lost through small leaks, maintenance, or airlock operations. Filters become contaminated. Chemical beds lose effectiveness. Membranes collect deposits. Sensors drift away from their original calibration. A system that worked beautifully during the first month may perform slightly worse during the 12th. The change may be too small for anyone to notice at first. Imagine a water recovery system designed to return most of the liquid used by the crew. At the beginning of the mission, its performance is comfortably within expectations. The tanks remain stable. The daily reports look reassuring. Then the efficiency begins to decline. Not dramatically. A fraction of a percent here. Another fraction months later. The system still works. The crew still drinks. No alarm sounds. But every percentage point of water that is not recovered must come from the reserves carried at launch. The spacecraft begins consuming those reserves faster than planned. The crew cleans the system. They replace a filter. They adjust the operating temperature. For a time, the numbers improve. Then they begin falling again. Earth receives the data and suggests new procedures, but no one can send a new membrane or a redesigned pump. The crew has only the parts aboard. Every repair consumes something. A replacement filter reduces the number remaining. A spare valve installed today cannot be installed again next year. A piece of equipment taken from a less important system may keep life support operating, but it leaves another part of the spacecraft incomplete. The ship slowly begins to cannibalize itself. A cable is borrowed from an experiment. A fan is removed from an unused storage compartment. A computer is shut down, so its power supply can be moved elsewhere. The vehicle still functions, but less of it exists in its original form. Each successful repair changes the spacecraft into something its designers never fully tested. This is where the crew's relationship with the machine becomes deeply personal. On Earth, most people use technology without needing to understand its internal life. A refrigerator stops cooling, and a technician repairs it. A water pump fails, and another is installed. Inside a distant spacecraft, the crew cannot afford that separation. They must learn every sound: the steady rhythm of a fan, the vibration of a pump, the click of a valve opening, the faint change in tone that suggests a bearing is wearing down. A noise that would be ignored inside a house may keep someone awake inside the spacecraft. Because the walls are not merely walls. They are part of the system that maintains pressure. The hum is not background noise. It is the sound of air moving toward the crew. Silence, in the wrong place, may mean something has stopped. Long missions also expose materials to stresses that are difficult to reproduce perfectly on Earth. Radiation slowly damages electronics. Repeated heating and cooling can weaken seals. Plastic becomes brittle. Lubricants degrade. Tiny particles of dust and debris enter moving components. Microorganisms grow in warm, damp areas and form films inside plumbing. A pump does not need to explode to become dangerous. It only needs to lose a little performance each month. A sensor does not need to fail completely. It only needs to report the wrong value convincingly. That may be more dangerous than reporting nothing at all. If an oxygen sensor goes dark, the crew knows there is a problem. If it quietly drifts and reports a safe number while the atmosphere changes, the crew may trust it. Deep space engineering is therefore not only about preventing failure. It is about recognizing failure before it becomes visible. The crew will spend part of every day inspecting the world that keeps them alive. They will measure air quality, test water, check power levels, listen for changes, compare current performance with records from months earlier. Maintenance will become a form of survival ritual. And the greatest threat may not be a dramatic accident. It may be accumulated wear. One system loses efficiency. That forces another system to work harder. The second system consumes more electricity. The power margin shrinks. Heaters are used less often. A cold line becomes harder to operate. A valve sticks. The crew applies extra power to free it. Another circuit overheats. No single failure destroys the spacecraft. Instead, small problems begin to connect. This is how complex machines often die. Not through one impossible event, but through several manageable events, arriving close enough together that the system can no longer absorb them. Near Earth, engineers can interrupt this chain with replacement hardware. In deep space, the crew must break the chain using only what remains aboard. Every decision becomes an exchange. Power for heat, water for shielding, a spare part for one system instead of another, time spent repairing machinery instead of sleeping. The spacecraft is a limited collection of matter, trying to remain a functioning world for longer than any of its individual components were meant to last. And the crew knows that the machine will never become younger. Even after a successful repair, the mission does not return to the day of launch. The new part is installed inside an older system. The reserves are smaller. The people are more tired. The journey is longer. The ship continues outward, carrying less margin than it had before. For a mission to Mars, this challenge lasts years. For a journey toward the giant planets, it could last decades. By then, survival would depend not only on carrying spare parts, but on manufacturing new ones aboard the spacecraft. Future crews may use advanced printers and machine tools to create simple components from stored material. They may recycle damaged equipment into raw metal or plastic. Intelligent diagnostic systems may help identify faults and suggest repairs, but manufacturing has limits. A printer cannot create a complex electronic chip without the right facilities. A machine cannot produce material it does not have. And every manufacturing system is itself another machine that can fail. There is no final escape from the problem. A closed spacecraft survives by consuming its own stored order. Its fuel becomes motion. Its food becomes human tissue. Its replacement parts become repairs. Its energy becomes heat, light, and breathable air. Nothing is truly renewed. Everything is transformed, degraded, or slowly lost. This is the fourth great protection removed by distance. Near Earth, civilization can continue rebuilding the spacecraft from the outside. Farther away, the spacecraft must rebuild itself from within. And eventually, there may come a failure for which no compatible part remains. No clever improvisation works. No unused system can be sacrificed. No instruction from Earth can change the physical inventory aboard. The crew will understand the problem. They may know exactly how to fix it. But understanding is not the same as having what the repair requires. The machine keeping them alive does not need to be perfect. It only needs to remain repairable. And the farther it travels, the fewer repairs it has left. Still, even the most reliable machinery requires energy. Pumps need electricity. Heaters need electricity. Computers, lights, radios, medical equipment, and air systems all depend on a continuous supply of power. Near Earth, sunlight feels almost endless. But as the spacecraft moves toward the outer solar system, the sun begins to shrink, and the energy that once seemed abundant starts disappearing far faster than human intuition expects. At Earth's distance, sunlight feels permanent. It rises every morning, warms the surface, drives the weather, feeds plants, powers solar panels, and fills the sky with enough energy that darkness seems temporary. A spacecraft near Earth can unfold broad wings of solar cells and collect more than enough electricity to run computers, instruments, heaters, radios, and life support systems. The sun appears dependable, but its power fades with distance far more quickly than intuition suggests. Sunlight follows the inverse square law. Move twice as far from the sun, and the same solar panel receives only 1/4 as much energy. Move 5 times farther away, and it receives only 1/25. At 10 times Earth's distance, just 1% remains. The sun itself has not weakened. Its energy is simply spreading across an ever larger sphere of space. Each square meter of that sphere receives less. Near Mars, sunlight is still strong enough for solar power, although panels must be larger and used more carefully. Beyond Mars, the decline becomes severe. By the time a spacecraft reaches Jupiter, sunlight is less than 4% as intense as it is near Earth. A panel that worked comfortably in the inner solar system now produces only a small fraction of its original power. To compensate, the spacecraft must carry much larger arrays. Those arrays add mass. They must unfold correctly after launch. They must survive years of travel, temperature changes, radiation, and tiny impacts. And even when they work perfectly, they are still collecting light from a sun that has become little more than a brilliant distant lamp. This is why the Juno spacecraft required enormous solar panels to operate around Jupiter. Its 3 long wings spread across a large area, yet together, they produce only a modest amount of electricity compared with what the same panels would generate near Earth. The design works because Juno is a robotic probe. It does not need breathable air. It does not need warm living spaces, cooking equipment, medical systems, exercise machines, or water recycling hardware. A human spacecraft would demand far more. Keeping several people alive requires a continuous flow of power. Air must circulate. Carbon dioxide must be removed. Water must be pumped and purified. Cabins must remain warm. Computers must monitor thousands of systems. Food must be stored safely. Communication equipment must transmit across hundreds of millions of miles. Every watt becomes part of the survival budget. And beyond Jupiter, sunlight continues to fall. At Saturn, it is roughly 1% as strong as at Earth. At Uranus, less than 0.3%. At Neptune, close to 1,000th. There, the sun still shines. It remains brighter than the other stars. But it no longer provides the flood of energy that shaped life on Earth. Solar panels become less like power plants and more like nets stretched into a nearly empty current. Past a certain distance, carrying larger panels stops being practical. The spacecraft must bring its own source of energy. For robotic missions, this has usually meant radioisotope power systems. Inside them, a small quantity of radioactive material releases heat as it naturally decays. That heat can be converted into electricity. There are no spinning turbines, no flame, no sunlight required. The source simply remains warm for years, producing a steady but limited amount of power. Voyager, Cassini, and New Horizons all depended on this principle. It allowed them to travel through regions where solar energy was too weak to support their missions. But radioactive power is not endless. Its output slowly declines. The material cools as the years pass. Electrical systems also become less efficient. The spacecraft begins life with a fixed energy inheritance, and every year that inheritance becomes smaller. Engineers respond by shutting systems down. First, an instrument is placed into permanent silence. Then a heater is turned off. Later, another sensor is sacrificed so that the transmitter can remain active. The spacecraft survives by becoming less capable. Its power source does not fail all at once. It simply offers a little less each year. This gradual decline would be far more serious for a human crew. A robotic probe can allow part of itself to freeze. It can stop taking pictures. It can spend months doing almost nothing. Human beings cannot. A living cabin must remain within a narrow range of temperature. The air cannot be allowed to become still. Water lines cannot freeze. Medical equipment cannot be abandoned simply because power is low. The crew may reduce lighting, scientific work, and communication, but there is a minimum beneath which the spacecraft stops being habitable. In the outer solar system, heat becomes as important as electricity. Space is often described as cold, but the vacuum itself does not cool a spacecraft the way cold air cools a person. There is almost no matter outside to carry heat away. Instead, the spacecraft loses energy by radiating it into space. Near Earth, sunlight can overheat a vehicle, so engineers must carefully reject excess warmth. Farther out, the balance reverses. The sun provides less. The spacecraft continues radiating. Without internal heat, its temperature begins to fall. At first, the cabin feels no different. Heaters quietly compensate. Then the power margin shrinks. A storage compartment is allowed to become colder. A corridor heater is reduced. A backup instrument is shut down. The crew begins living inside a smaller island of warmth. Outside that island, the spacecraft slowly freezes. Propellant lines become difficult to keep above their operating temperature. Lubricants thicken. Batteries lose performance. Materials contract. Electronics behave differently. A valve that opened easily near Earth may become reluctant after years in the outer darkness. The cold does not attack. It waits for the heaters to lose. Then comes Jupiter. After watching sunlight fade for years, the crew approaches a world with a magnetic field far stronger than Earth's. Jupiter's magnetosphere traps enormous numbers of energetic particles, creating radiation belts capable of damaging spacecraft electronics and delivering lethal doses to unprotected humans. The irony is almost perfect. Near Earth, a magnetic field is part of what protects you. Near Jupiter, a magnetic field becomes part of what threatens you. A human vehicle approaching the giant planet would need heavy shielding, carefully chosen orbits, and strict limits on how long it remained in the most dangerous regions. Water tanks and supplies might be arranged around living areas to absorb radiation. The ship could pass quickly through intense zones rather than remain there. But shielding adds mass. Mass requires more propulsion. More propulsion requires more fuel. And every additional system requires more power from a sun already growing weak. The farther the mission travels, the problems begin to reinforce one another. Distance reduces sunlight. Reduced sunlight requires a different power source. That source has limited output. Limited power makes heating more difficult. Radiation demands heavier shielding. Heavier shielding makes the vehicle harder to move. Longer travel times allow equipment more time to age. Nothing exists as a single problem. Every solution becomes part of another calculation. Beyond Jupiter, the local radiation environment becomes calmer again. Saturn hangs ahead with its rings. Uranus turns quietly in the dark. Neptune waits near the edge of the planetary system. These worlds are magnificent, but reaching them takes years. A crew traveling that far would watch the sun shrink until it no longer looked like the object that once filled the days of Earth. It would be a brilliant point, still visible, still home, but unable to warm the spacecraft without help. This is the fifth protection lost on the journey outward. The sun does not disappear. It becomes insufficient. Its light remains beautiful long after it stops being useful. And eventually, the crew would realize that every degree of warmth around them was no longer coming from the star behind the window. It was coming from fuel carried from Earth. From radioactive heat, from electrical resistance, from a finite store of energy slowly being spent to hold back the dark. Past Neptune, even the last major planet falls behind. The sun becomes smaller still. The spacecraft continues into a region often imagined as crowded with frozen worlds, but the reality is emptier. Ahead lies an ocean with almost no islands, and the few islands that do exist offer no shelter at all. Beyond Neptune, the architecture of the solar system changes. The great planets are behind you. No enormous world remains ahead to dominate the sky. No broad rings catch the sunlight. No familiar sequence of destinations waits along the route. The spacecraft enters the Kuiper Belt, a distant region filled with icy bodies left over from the formation of the solar system. From diagrams, the Kuiper Belt can appear crowded. It is often drawn as a thick band of objects surrounding the sun, as though a traveler leaving Neptune would immediately enter a field of tumbling ice. The reality is almost the opposite. The Kuiper Belt contains countless objects, but it occupies an enormous volume of space. The distances between its larger members are vast. A spacecraft can travel for years through the region without passing near anything substantial. There are no walls of frozen debris, no constant need to dodge dwarf planets, no glittering landscape of nearby worlds. There is mostly darkness. Pluto is one of the better-known inhabitants of this region, but even Pluto does not feel like a destination in the ordinary sense. It is small. Its atmosphere is thin and temporary, expanding when it moves closer to the sun and collapsing toward the surface as it travels farther away. Its mountains are made partly of water ice, which at Pluto's temperature behaves more like stone. Its plains contain frozen nitrogen. Its sunlight is dim enough that the sun appears as a brilliant star rather than a disk dominating the sky. And yet, even there, the sun is still much brighter than a full moon seen from Earth. A person standing on Pluto at noon, protected by an impossible suit, would not be surrounded by total darkness. There would be shadows. The landscape would be visible. The horizon would glow beneath a weak but recognizable day. This is one of the strange lessons of the outer solar system. The sun becomes useless as a major power source long before it becomes invisible. It can still illuminate a world that it can no longer warm. A spacecraft moving beyond Pluto would continue past other frozen bodies, each separated by distances that make the word neighborhood feel misleading. Some are large enough to be nearly round. Others are irregular fragments. Many are so dark that they reflect only a small fraction of the sunlight reaching them. Their surfaces may preserve material unchanged for billions of years. They are ancient. They are scientifically valuable. But they are not ports. A ship reaching one of these worlds would find no breathable atmosphere, no liquid ocean on the surface, no fuel depot, no prepared shelter, and no source of warmth waiting to be used. Landing would not solve the problem of isolation. It would only transfer the crew from one hostile machine to another hostile environment. The surface might contain water ice, but extracting it would require equipment, energy, and time. The ice would have to be mined, melted, purified, stored. Every step would depend on machines already carried aboard the spacecraft. The world itself would provide raw material, but not safety. This is an important distinction. On Earth, islands once offered sailors wood, water, food, and a place to rest. Even a remote shore could extend a voyage. In the outer solar system, an island of rock and ice offers almost nothing in a form the human body can use. There is no natural harbor, no open fire, no air, no place where the machinery of survival can be switched off. The crew may stand on a new world, but they remain entirely dependent on the ship. Farther out, the Kuiper Belt begins to thin. The sun's influence continues, but the visible structure of the planetary system fades. The spacecraft enters a region that may contain scattered icy bodies on extremely long orbits. Far beyond them lies the theoretical Oort cloud, a vast reservoir of comet-like objects believed to surround the solar system in a distant shell. No spacecraft has reached it. No telescope has directly mapped it in detail. Its existence is inferred from the orbits of long-period comets that occasionally fall inward toward the sun. If the Oort cloud is shaped roughly, as current models suggest, its outer edge may extend a significant fraction of the way to the nearest stars. This means the solar system may not end cleanly. There may be no final planet, no last rock, and no single obvious point where the sun's family of orbiting objects simply stops. Instead, the system dissolves gradually into interstellar space. Objects become rarer. Their orbits become wider. The distinction between belonging to the sun and merely passing nearby becomes less clear. For a traveler, this creates an unsettling geography. There is no final coastline, no moment when the familiar map ends and a new map begins. The destinations simply become farther apart until there are effectively none. Communication has also changed by now. A radio signal from the region of Pluto takes hours to reach Earth. A question and its reply may require most of a day. Farther into the scattered disk, the delay grows longer. The crew can still send data. Earth can still respond. But the exchange begins to resemble letters, carried across an ocean, rather than a conversation between members of the same mission. A mechanical problem appears in the morning. The crew documents it, sends the report, and spends the day working without an answer. Earth receives the message many hours later. Engineers study the problem while the spacecraft continues farther away. Their response begins its return journey. By the time it arrives, the crew may be asleep, or the problem may have changed, or the component may already have failed. The distance does not prevent communication. It slowly removes usefulness from it. The same is true of rescue, only more completely. A crew near Neptune is not merely far from Earth. It is separated from Earth by years of travel. Even if a rescue vehicle were prepared and launched immediately, it could not arrive within any timescale relevant to an emergency. A broken bone would heal before help came. A fire would end. An infection would resolve or kill. A failing life support system would either be repaired by the crew or become fatal long before another spacecraft crossed the distance. Rescue has ceased to be an operational possibility. It survives only as an idea. The people aboard know this. Every morning, they wake inside the only reachable human environment for billions of miles. Every face they see belongs to someone already aboard. Every voice from Earth arrives from the past. Every tool they may ever use is stored somewhere inside the ship. There will be no new room, no new person, no unexpected delivery, no weekend away from the crew. This isolation becomes its own environment. Human beings are remarkably adaptable, but adaptation does not eliminate friction. In a small group living together for years, every habit becomes visible. The way someone eats, the time they spend in the hygiene compartment, the way they breathe when nervous, the music they play too often, the phrase they repeat when tired. On Earth, irritation can be softened by distance. A door can be closed. A walk can be taken. A person can leave the building and spend an evening among strangers. In a deep space vehicle, no true separation exists. The crew may have private sleeping compartments, but the walls are thin and the volume is limited. The same people share every emergency, every meal, every celebration, and every silence. A disagreement cannot be escaped. It can only be managed. The crew becomes more than a team. It becomes an entire society, reduced to a handful of individuals. Someone will emerge as the calmest voice. Someone may become withdrawn. Two people may form a close alliance. Another may feel excluded. Old conflicts may disappear and return months later in different forms. None of this means the crew is unqualified. It means they are human. The farther the spacecraft travels, the fewer outside influences remain to interrupt these patterns. No new colleague joins. No visitor arrives. No change of scenery occurs beyond the slow rearrangement of stars through the windows. Even entertainment is finite. Books can be reread. Films can be watched again. Messages from Earth can arrive. Virtual environments may create the illusion of forests, oceans, or city streets. But the crew knows that every image of home is stored light. Nothing in the room is alive except the people and the microorganisms traveling with them. The days continue. Maintenance, exercise, meals, scientific work, sleep, a new problem, a successful repair, another message from Earth, another month farther from the sun. Outside, the spacecraft crosses an ocean without waves and without islands. There may be objects nearby by astronomical standards, but none are close enough to matter. The emptiness is not absolute. It is simply too large for the available speed. This is the sixth protection lost during the outward journey. The idea of a nearby destination disappears. Near Earth, there is always another orbit, another station, another planet ahead. Beyond Neptune, the word ahead begins to lose meaning. A course may point toward a known object, but reaching it may take years. A small error in direction may become millions of miles of separation, and a spacecraft not aimed at anything in particular will not casually encounter a replacement destination. The ocean is too wide. The islands are too small. The traveler continues outward, still technically within the sun's domain. The solar wind still flows past the hull. The sun's magnetic field still shapes the particles around the ship. Even here, among the distant frozen remnants of planetary formation, the spacecraft has not fully escaped its star. But that influence is weakening. Far ahead lies a boundary no human eye could recognize. There is no light around it, no surface, no sign, only a change in the invisible particles surrounding the ship. On one side, the environment is still shaped by the sun. On the other, the spacecraft will enter material drifting between the stars. It will cross beyond the sun's final breath. For almost the entire journey so far, one invisible fact has remained true. The spacecraft has been traveling inside the sun, not inside its visible surface, not inside the glowing corona seen during a total eclipse, but inside a much larger structure created by the sun's continuous outflow of charged particles. Every second, the sun releases a stream of protons, electrons, and magnetic fields into space. This solar wind moves outward in all directions, passing Earth, Mars, Jupiter, Neptune, and the frozen worlds beyond. It shapes comet tails. It disturbs planetary magnetospheres. It drives auroras. And it fills a vast bubble around the entire solar system. That bubble is called the heliosphere. Every human being who has ever lived has spent their entire life inside it. Every planet visited by a spacecraft lies within it. Every moon landing, every Mars rover, every telescope orbiting Earth, every radio message sent between worlds has taken place inside the sun's extended influence. The heliosphere is not visible. A traveler cannot look through a window and see its boundary approaching. There is no glowing shell around the solar system, no surface, no edge sharp enough to touch. Instead, the boundary is defined by pressure. The solar wind pushes outward. The thin material between the stars pushes inward. Far from the sun, these two environments meet. The solar wind slows. It becomes disturbed and compressed. Eventually, it can no longer dominate the space around it. The boundary, where the sun's wind finally gives way, is called the heliopause. Only 2 functioning spacecraft have ever crossed it. Voyager 1 crossed first. Voyager 2 followed years later. Neither spacecraft saw anything dramatic. There was no flash, no collision, no sudden change in the stars. The transition was discovered through instruments. Particle counts changed. The direction and character of magnetic fields shifted. The density of surrounding plasma increased. The spacecraft entered matter that was no longer primarily controlled by the sun. This may be one of the quietest great crossings in the history of exploration. A machine built on Earth passed beyond the region governed by its own star, and the universe marked the event only with a few changing numbers. Imagine a crew approaching the same boundary. By this point, the sun has already shrunk into a brilliant point behind them. Its light still reaches the ship. Its gravity still reaches the ship. But its warmth is gone. The planets are invisible. Earth cannot be seen without powerful instruments. The entire inner solar system occupies a region of sky too small to distinguish with human eyes. Ahead, nothing appears different. The crew continues their routines. They repair equipment, monitor air, exercise, sleep, listen for changes in machinery. Then, one day, the instruments begin reporting a new environment. The plasma outside is denser. The pattern of charged particles changes. The magnetic field no longer behaves as it did inside the heliosphere. The crew has crossed beyond the sun's final breath. For the first time in human history, people would be moving through material that belongs to the space between stars. This would not necessarily make the immediate environment more violent. Interstellar space is not a storm. It is not filled with dense clouds waiting to crush the spacecraft. The local interstellar medium is extraordinarily thin. A cubic centimeter may contain only a small number of particles. The ship would not feel resistance. No wind would shake the hull. No sound would enter the cabin. But the meaning of the surroundings would change completely. Inside the heliosphere, the sun was always more than a light in the distance. It was the central authority of the environment. Its wind shaped the space around the spacecraft. Its magnetic influence altered the radiation passing through the solar system. Its activity changed the conditions from one year to the next. Beyond the heliopause, the sun loses that role. It becomes one star among hundreds of billions, still special to the crew, still the source of every familiar memory, but no longer physically dominant where they are. The particles outside the hull now come from a larger galactic environment. Some drift from nearby stars. Some carry the history of ancient supernova explosions. Some have wandered through the Milky Way for millions of years before meeting the spacecraft. The ship is no longer surrounded by the breath of home. It is surrounded by the galaxy. This is the point at which the emotional meaning of distance changes again. Until now, the crew has been traveling outward through the solar system. No matter how dark the surroundings became, they were still inside a structure with the sun at its center. The planets behind them belonged to the same system. The frozen bodies ahead still orbited the same star. There was still a kind of geography. Beyond the heliopause, that geography dissolves. The crew has not reached another star system. They have simply left their own, and the nearest replacement is unimaginably far away. From Earth, the stars appear to cover the sky. Thousands can be seen on a clear night. They seem crowded. Some appear close enough to form patterns, but those patterns are an illusion created by distance and perspective. The stars in a constellation may be separated from one another by hundreds of light years. They appear side by side only because the human eye cannot sense depth at such scales. Beyond the solar system, this illusion becomes deeply unsettling. The sky may still contain countless points of light, but none of them is nearby. The nearest star to the sun is more than 4 light-years away. Light itself requires more than 4 years to cross that distance. A spacecraft moving at the speed of Voyager would need tens of thousands of years to reach it. And Voyager is not even traveling toward that star. It is moving along a path determined decades ago, crossing a region with no close destination ahead. This is where leaving the solar system becomes more than a symbolic achievement. It becomes an irreversible commitment to emptiness. A spacecraft cannot simply turn around like a boat. To reverse direction, it must first cancel its outward velocity. Then it must accelerate back toward the sun. That requires an enormous change in speed. A crewed vessel would need fuel not only to travel outward, but to erase years of accumulated motion and begin the journey home. At interstellar distances, the required energy becomes overwhelming. The vehicle may still have engines. It may still be able to adjust its course, but a small correction is not the same as return. The ship has crossed a boundary, after which home remains visible in principle, but unreachable in practice. The sun still shines behind them. Yet reaching it again may demand more fuel than the spacecraft could ever carry. This is the seventh protection lost on the journey outward. Not sunlight, not communication, not rescue. The possibility of reversal. Every explorer before this point could imagine turning back. A sailor could change course. A polar expedition could retreat. An astronaut near the moon could return within days. A crew near Mars might wait for the correct planetary alignment and eventually travel home. But beyond the heliopause, aboard a ship already committed to interstellar flight, turning around may no longer be a real option. The crew has not entered a more dangerous physical environment. They have entered a one-way future. Communication with Earth continues, but the delay now stretches across most of a day. A message is transmitted. Hours pass. Earth receives it. A response is prepared. More hours pass. By the time the reply arrives, the ship has moved farther outward, and the crew has lived through another cycle of work and sleep. The people on Earth are no longer monitoring a mission in the present. They are reading a record of a life unfolding almost a day earlier. Farther out, the delay becomes several days, then weeks, then months. The crew sends reports that describe seasons no longer occurring aboard the ship. Earth sends news that arrives long after it ceased to be news. Births, deaths, celebrations, political changes, scientific discoveries, all cross the darkness as delayed fragments of a world continuing without them. Eventually, the crew may receive a message recorded by someone who has since died. Earth may receive a reply from a person who did not live long enough to hear the next response. Communication becomes less like conversation and more like archaeology. Each side studies the recent past of the other. Yet this boundary is not the end of the journey. It is only the moment the true scale of interstellar space becomes clear. Behind the spacecraft, the sun is one bright star. Ahead, the next star is still years away even for light. Between them lies a darkness so vast that a human lifetime barely crosses the first fraction of it. Leaving the sun does not bring the traveler closer to another world. It reveals how far away every other world has always been. Beyond the heliopause, the spacecraft is finally traveling through interstellar space. The phrase sounds as though it describes a place between destinations, a corridor from one star to the next. But a corridor suggests walls, direction, and an exit visible somewhere ahead. Interstellar space offers none of those things. It is not a road connecting neighboring worlds. It is an abyss in which the worlds are almost impossibly far apart. The nearest star system to the Sun, Alpha Centauri, lies a little more than 4 light-years away. That distance is often stated so casually that it can lose its meaning. Light moves fast enough to circle Earth more than 7 times in a single second. Yet even light needs more than 4 years to reach our nearest stellar neighbor. A radio message sent from Earth today would arrive there years later. A reply, if one were sent immediately, would not return for more than 8 years. And light is far faster than any spacecraft humanity has ever built. Voyager 1 moves through interstellar space at roughly 11 miles per second relative to the Sun. That is astonishing by human standards. It could cross an ocean in minutes. But at that speed, a journey of 4 light-years would take tens of thousands of years. The spacecraft would outlive languages. Nations would rise and disappear. Coastlines would change. Human beings might become something entirely different before the vehicle came close to another star. And Voyager is not aimed at Alpha Centauri. It is not aimed at any nearby star that it could reach on a useful timescale. It is simply moving outward, along the direction created by its encounters with the giant planets many decades ago. This reveals one of the most unsettling facts about interstellar travel. Leaving a star does not mean another star is waiting nearby. The sky may appear full, but fullness is an illusion. The stars are bright enough to be seen across enormous distances, which makes the galaxy look crowded from Earth. Once you begin crossing those distances, the crowd disappears. Imagine a map showing every star within dozens of light years. On paper, they may look like points scattered close together. Now imagine expanding the map until the distances are represented honestly. The points move apart. The page becomes a room, then a city, then a continent. The stars remain tiny. Most of the map becomes empty space. A traveler crossing it would spend almost the entire journey seeing no nearby world, no planetary system, and no obvious evidence of progress. The star behind would slowly dim. The star ahead would slowly brighten. But for centuries, perhaps millennia, both changes might be almost impossible to notice without instruments. The view outside the window would remain nearly unchanged across many human lifetimes. This is a different kind of isolation from anything inside the solar system. Near Mars, there is at least a planet ahead. Near Jupiter, a giant world grows visibly larger. Beyond Neptune, the sun still defines the direction home. Between stars, both departure and arrival become abstract. The spacecraft may be moving at tremendous speed, yet the surrounding sky appears frozen. There is no landscape passing beneath it, no sensation of motion, no wind, no nearby object against which speed can be judged. Inside the cabin, the crew feels stationary. Only the navigation computer confirms that the ship is crossing millions of miles each day. And even those millions barely matter. Interstellar distance consumes them without appearing to change. The space between stars is not perfectly empty. It contains thin gas, dust, magnetic fields, and high-energy particles. Most of this material is so sparse that the spacecraft could travel for years without collecting enough of it to fill a drinking glass. But at high speed, even sparse material becomes important. A grain of dust moving slowly through the galaxy may be harmless on its own. If a spacecraft strikes it at a significant fraction of the speed of light, the collision can release enormous energy. The grain does not need to be large. Velocity transforms it. A fleck smaller than sand may strike like an explosive. Individual atoms can damage surfaces, erode shielding, and create radiation as they collide with the front of the ship. The faster the spacecraft travels, the more dangerous the emptiness becomes. This produces another cruel trade-off. Slow travel makes the journey last too long for human beings. Fast travel turns the rare particles ahead into a continuous hazard. A truly interstellar vehicle may require thick forward shielding, magnetic defenses, layers of sacrificial material, or systems capable of detecting larger objects far enough ahead to change course. But detecting dark objects in interstellar space is difficult. A planet without a star may drift through the galaxy almost invisibly. These rogue planets do not reflect much light because there is little nearby light to reflect. Some may have been thrown out of young planetary systems. Others may have formed alone. There could be billions of them in the Milky Way. Most would never pass close to a spacecraft. The galaxy is too large. But that is not entirely reassuring. Their darkness means that a traveler might not know one was nearby until its gravity began to influence the route, or its faint heat became detectable. Brown dwarfs are larger and warmer than planets, but too small to sustain ordinary hydrogen fusion like stars. They may also wander through the darkness with little visible light. Again, the chance of accidentally approaching one is extremely small. Interstellar space is not crowded with hidden objects waiting to ambush a ship. The deeper horror is the opposite. The traveler is unlikely to encounter anything at all. A rogue planet might sound frightening, but a rogue planet would at least be somewhere. It would provide gravity, material, perhaps buried ice, and a position on a map. Most interstellar journeys offer only distance. Even the dangerous objects in the galaxy are separated by enormous gulfs. A neutron star may contain more mass than the Sun compressed into a sphere roughly the size of a city. Its gravity near the surface is extreme. Some rotate rapidly, sweeping beams of radiation across space, like cosmic lighthouses. Magnetars possess magnetic fields so powerful that a sufficiently close encounter would disrupt atoms and destroy electronics long before the star appeared large in the sky. Supernova remnants accelerate particles. Gamma-ray bursts can send focused waves of high-energy radiation across thousands of light-years. But these events are rare, and careful navigation could avoid known dead stars. They are not the main experience of interstellar flight. The main experience is waiting. The same maintenance routines repeated across years. The same stars beyond the glass. The same destinations still impossibly far ahead. Generations might be born inside the spacecraft without ever seeing the star their ancestors left, or the one their descendants hope to reach, as anything more than points of light. For them, the ship would no longer be a vehicle. It would be the entire known world. Earth would become history. The sun would become a story. Oceans, forests, rain, and open skies would survive as recordings and descriptions of environments no living crew member had ever touched. Eventually, even the idea of traveling somewhere might change. The first generation would remember leaving. The second would understand the mission through their parents. The 10th might see the destination as a belief inherited from people who lived centuries earlier. They would maintain systems built by ancestors whose names had become labels in technical manuals. A repair procedure might be followed not because anyone understood every original decision, but because the ship had survived by following it for generations. One mistake could damage a system that had worked longer than any living person had been alive. One forgotten piece of knowledge could become more valuable than any remaining physical resource. This is the 8th protection removed by distance. The journey loses a destination that can be reached within a human life. Near Earth, travel is measured in hours. Mars requires months. The outer planets require years. Another star may require millennia. Distance has now exceeded biology. The universe has not placed an impenetrable wall between the stars. It has done something more effective. It has made the space between them so large that a human lifetime becomes almost irrelevant. And even this abyss is not the greatest emptiness in the universe. The Milky Way still surrounds the traveler. Hundreds of billions of stars still fill the galaxy. However isolated the spacecraft may feel, it remains inside a vast island of light. But beyond the edge of that island lies a darkness on an entirely different scale. A place where the nearest stars are not light years away. They are millions of light years behind. The Milky Way is enormous by every human measure. It contains hundreds of billions of stars spread across a disk roughly 100,000 light years wide. From within it, the galaxy seems almost limitless. A spacecraft could travel for thousands of years and still remain in the same small neighborhood of stars. But the Milky Way is not the universe. It is an island, and beyond its outer regions lies an ocean far greater than the space between one star and the next. Imagine that the spacecraft continues outward for longer than any civilization has ever existed. The familiar constellations distort. Nearby stars shift across the sky. The dense band of the Milky Way begins to change shape as the traveler rises above the galactic disk. At first, the galaxy still surrounds the ship. Stars appear in every direction. Then the view slowly opens. From far above the disk, the Milky Way would no longer look like a bright river crossing the sky. It would become a structure beneath the traveler, a broad spiral of light, dust, gas, and dark matter turning slowly through space. The central region would glow more intensely. Spiral arms would curve outward. Dark lanes of dust would cut through the starlight. For the first time, the traveler could see the galaxy as a whole. It would be one of the most beautiful sights any human mind could imagine. And then it would begin to shrink. Leaving a galaxy is far more difficult than leaving a star. The sun's gravity dominates the solar system, but the Milky Way is held together by the combined gravity of stars, gas, black holes, and an enormous halo of dark matter. A spacecraft would need extraordinary speed to escape. Even if that speed were achieved, the journey from the galactic disk into true intergalactic space could take millions of years. Generations would pass before the bright island behind the ship became small. Eventually, the individual stars would merge into a pale glow. The spiral structure would remain visible through instruments, but the naked eye would see something more like a distant cloud suspended in darkness. Everything the traveler had ever known would be contained inside it. Earth, the sun, every star visible from the night sky, every world humanity had visited, every human voice ever transmitted into space. All of it reduced to one faint island behind the spacecraft. Ahead lies intergalactic space. The matter there is even thinner than the material between stars. Individual atoms may be separated by enormous distances. Vast regions contain almost no stars at all. There are no nearby planetary systems, no rogue worlds drifting within reach, and no bright stellar landmarks against which motion can easily be measured. The nearest substantial objects are other galaxies, and they are not light years away. They are millions of light years away. The Andromeda Galaxy, one of the nearest large galaxies to the Milky Way, is roughly 2.5 million light years from Earth. Light leaving Andromeda today began its journey before modern humans existed. A spacecraft traveling at the speed of Voyager would require tens of billions of years to cross that distance. Even a ship moving at a significant fraction of the speed of light would spend generations in transit. The darkness between galaxies is therefore not simply a larger version of the darkness between stars. The scale changes the meaning of travel itself. Inside a galaxy, there are always other stars, even when they are impossibly distant. Between galaxies, the entire stellar landscape can fall behind. The traveler may look outward and see many galaxies through powerful instruments, but none would grow visibly larger for ages. The Milky Way behind would slowly fade. The destination ahead would remain a dim patch of light. For millions of years, the spacecraft would exist between islands without being meaningfully close to either. And some regions of the universe are even emptier. Galaxies are not distributed evenly. They gather into groups, clusters, filaments, and enormous walls surrounding vast, low-density regions known as cosmic voids. Some voids stretch across hundreds of millions of light-years. They are not completely empty. A few faint galaxies may exist within them. Thin gas and dark matter remain. But compared with the luminous structures surrounding them, these regions contain remarkably little. A traveler deep inside such a void would see a different universe. The nearest large galaxies might appear faint and widely separated. The sky would not glow with a dense network of nearby cosmic structures. Most directions would lead through immense distances before reaching anything bright. If a civilization had evolved on a rare world near the center of a great void, It might have taken far longer to discover that galaxies form clusters and filaments. Its night sky would provide less evidence of the universe's large-scale architecture. Cosmic isolation would shape not only travel, but knowledge. For our hypothetical traveler, the void creates the most complete loss of direction yet. Near Earth, home was a blue planet. Beyond the solar system, home was a bright star. Between stars, home was the direction of the sun. Outside the galaxy, home became a spiral of light. Inside a cosmic void, even that spiral may be one faint galaxy among many, difficult to distinguish across distances, too large for intuition. The traveler could know the coordinates. The navigation systems could remember the path. But the human eye would no longer find anything in the sky that felt like home. Distance has now erased the visible thread, and the universe is still expanding. Space itself grows between distant galaxies. This does not mean galaxies are flying through a fixed emptiness like fragments from an explosion. On the largest scales, the distances between unbound regions increase because the geometry of space changes over time. Nearby galaxies held together by gravity may remain connected, but sufficiently distant galaxies recede from one another as the universe expands. The farther away a galaxy is, the faster the distance between us, and it generally grows. This leads to a final kind of boundary. There are regions so distant that the expansion of the universe prevents any signal sent today from ever reaching them. Their light may still be arriving now because it began its journey long ago when those regions were closer. But a message sent toward them in the present would never arrive. The space between would expand too quickly. This is not a barrier made of matter. There is no wall to strike, no edge where a spacecraft stops. The destination remains visible. Its ancient light continues to enter the telescope, yet its future has become unreachable. This may be the most unsettling form of distance in the universe. Near Mars, distance delays a reply. Between stars, distance exceeds a lifetime. Between galaxies, distance exceeds civilizations. At the cosmic horizon, distance removes the possibility of arrival entirely. A galaxy can exist. You can see it. You can measure its light. You can know its chemical composition, estimate its mass, and study stars that lived there billions of years ago. And still, no traveler leaving now could ever reach it. Some parts of the visible universe are not destinations. They are records, images of places that have already slipped beyond any future connection. As cosmic expansion continues, more distant galaxies will fade from view. Their light will be stretched to longer wavelengths. Their signals will weaken. Far in the future, observers remaining inside the gravitationally bound local group may see fewer and fewer galaxies beyond it. The wider universe will not have vanished. It will simply have moved beyond the horizon from which light can reach them. The cosmos will appear smaller because distance has hidden the rest. This is the ninth and final protection lost on the outward journey, the assumption that every visible place belongs to the same reachable universe. Close to Earth, every light in the sky feels like a possible destination. Far enough away, even visibility becomes misleading. You may see where a galaxy was. You may receive the last ancient photons it will ever send you. But no action you take can create a future meeting. The universe has not destroyed the destination. It has removed the connection. Now the spacecraft hangs in the darkness between galaxies. Behind it, the Milky Way is a faint island. Ahead, other islands recede across expanding space. The crew has traveled beyond atmosphere, magnetic shelter, immediate communication, rescue, resupply, useful sunlight, nearby destinations, and the physical authority of the sun. They have crossed distances longer than lives, histories, and species. And at last, they have reached a place where distance does not merely make the journey difficult. It makes some journeys impossible. Nothing is chasing the spacecraft. Nothing is waiting in the darkness. The universe is doing only what it has always done, expanding, cooling, and quietly separating everything that is not strong enough to remain connected. At the beginning of this journey, space seemed frightening because it was empty. There was no air, no pressure, no warmth except what the spacecraft carried with it. A thin wall separated the crew from a vacuum that could end a human life in seconds. But near Earth, the danger was softened by connection. The planet's magnetic field still surrounded the ship. Mission control still answered in real time. A rescue capsule could still return the crew home. Food, medicine, and replacement parts could still arrive from the ground. The astronauts were in space, but they were not yet truly beyond the human world. Then the spacecraft continued outward, and with every new distance, something disappeared. First came the magnetic shelter. Beyond it, radiation no longer belonged mainly to the planet to manage. The spacecraft had to defend itself with water, supplies, carefully chosen materials, and whatever mass its designers could place between the crew and the invisible particles passing through the hull. A solar storm did not need to shake the ship. It did not need to darken the sky. The sun could look perfectly calm while radiation monitors climbed inside the cabin. Farther away, Earth lost the ability to speak in the present. A delay of seconds became minutes. Minutes became hours. Mission control could still offer knowledge, but it was always responding to a version of the spacecraft that no longer existed. The crew sent questions into the future and received answers written for the past. Then rescue disappeared. An ordinary medical problem became dangerous, not because the human body had changed, but because the nearest hospital had become unreachable. A voice could cross the distance. A doctor could not. A spacecraft could continue sending telemetry, while the people inside faced an emergency that no launch from Earth could reach in time. Next came resupply. Every component aboard became part of a closed inventory. A filter used today could not be replaced next year unless another had already been packed. A forgotten tool might as well never have existed. The spacecraft survived by repairing itself, rearranging itself, and slowly consuming the materials that had made survival possible in the first place. Then even the sun began to fail. Not as a star, not as a point of light, but as a useful source of power and heat. It remained visible long after its energy had become too weak to sustain the ship. The crew could look back and still see home star shining in the darkness, while every degree of warmth around them came from a finite source carried aboard. Beyond the planets, destinations began to disappear. The Kuiper Belt was not a crowded field of nearby worlds. The Oort cloud was not a chain of islands. There were objects, but they were scattered through distances so large that a spacecraft could travel for years without approaching anything substantial. Landing on a frozen world would not mean safety. It would only mean bringing the machinery of survival onto another place that could not support life. At the heliopause, the sun lost its final physical authority. The spacecraft entered material drifting between stars. Behind it, the sun was still bright. Still familiar. Still home. But it was no longer shaping the environment around the ship. It had become one star among hundreds of billions. Then came the interstellar abyss. The stars that looked crowded from Earth revealed their true separation. The nearest destination lay years away for light, and thousands of years away for machines. A spacecraft could move faster than anything humans had ever built, and still spend generations crossing a distance that barely changed the sky outside. Finally, even the galaxy fell behind. The Milky Way became a shrinking island of light. The space between galaxies opened ahead, and on the largest scales, the universe itself began removing destinations from the future. Some galaxies could still be seen because their ancient light had already crossed the distance. Yet no signal sent now could ever reach them. They were visible, measurable, and permanently inaccessible. This is the shape of the horror. It is not a monster hiding beyond Neptune. It is not a wall at the edge of the solar system. It is not a violent region where the laws of physics suddenly become cruel. The laws remain the same. Vacuum is vacuum. Light still travels at the same speed. Gravity still follows the same rules. Matter still behaves according to the same quiet patterns. What changes is how much of the human world can still reach you. Near Earth, the planet is everywhere. It surrounds you with protection. It listens. It watches. It sends help. Farther away, Earth becomes a delayed voice. Then, a distant memory. Then a star too faint to distinguish from the others. The universe does not need to hunt the traveler. It does not need to place traps along the route. Distance performs the work slowly enough that each loss can feel almost ordinary. A message takes a little longer. A repair uses the last spare. A heater is turned down. The sun becomes slightly smaller. A familiar galaxy fades behind the ship. No single moment needs to feel like the end. The horror comes from accumulation, from realizing that every threshold crossed has closed behind you, and that the things once taken for granted were never permanent features of space. They were gifts of proximity. Air was a gift of the planet. Protection was a gift of the magnetic field. Immediate voices were a gift of being close enough for light to return quickly. Rescue was a gift of short distance. Warmth was a gift of the sun. Destinations were a gift of living inside a crowded galactic island. Home felt permanent only because almost every human life had unfolded close enough to touch it. The traveler who continues outward eventually reaches a place where none of those gifts remain. The ship still moves. The stars still shine. The universe may be calmer than many regions already crossed. But calm is not the same as safe. Silence is not the same as peace. And beauty is not the same as belonging. Far enough from Earth, the most frightening realization is not that the universe wants you dead. It is that the universe has no reason to notice whether you live. It does not grow darker because you are afraid. It does not shorten the distance because you are tired. It does not return a message faster because someone aboard is dying. It does not place another world ahead simply because the journey has lasted too long. The spacecraft continues because motion continues. The distance grows because there is nothing to stop it. And the world that created the traveler becomes smaller with every passing second. This is why space grows more horrifying the farther you travel. Not because more dangers are waiting in the darkness, but because fewer things remain capable of reaching you. And far enough from home, the universe does not need to destroy you. It only needs to let you keep going.